Hello grade 11s. This is the final lesson in the series on wavefronts. We'll see how diffraction provides us with information about the stars and what they are made of. Now you remember that diffraction of light means the bending of light around an edge, or spreading out of light as it passes through a small gap. In lesson 2 and 3, we saw that we can explain diffraction if we accept Huygens' theory that light travels forward as a wave. Each point on a wave acts as a source of wavelets. The wavelets spread out in the forward direction, and the leading edge of all the wavelets forms a new wavefront. We also saw what happens to the wavefronts as they pass through a narrow slit. They travel forward as curved wavefronts. If the slit is wide, the wavefronts are not diffracted very much. But as the slit becomes very narrow, the wavefronts are diffracted at a wider angle. Here you see a beam of light from a red laser pass through a very narrow slit. The width of the slit can be adjusted. Watch what happens as the slit gets narrower. The bright and dark fringes spread out at a wider angle as the slit gets narrower. Why do we see diffraction fringes at all? The wavefronts coming through the slit set up interference patterns which we can see on the screen. If the waves reach the screen exactly in phase, then they strengthen each other and we see a bright line there. But in places where the wavefronts reach the screen out of phase, they cancel each other and we see a dark line there. Also, if we increase the wavelength of the light that goes through the slit, the diffraction angle increases. Red light has a longer wavelength than blue light. Then we can decrease the wavelength by using blue light, which has a shorter wavelength than red light. Here you can see how the diffraction spread compares for a long wavelength of red light and the short wavelength of blue light. So red light is diffracted more than blue light. This allows us to separate the colors of light and investigate them separately. In lesson 3, we found a relationship that we can write as sine theta equals the wavelength lambda divided by the slit width w. This is just what scientists want, mathematical relationships that give them methods to make measurements. The diffraction fringes from a single slit are not very bright or clear because not much light can get through a slit that is a tiny fraction of a millimeter wide. An answer to that problem is to use a diffraction grating, which has thousands of slits very close together. They are so narrow that you can see them only under a microscope. The grating lets through thousands of times more light and we can see quite bright diffraction patterns. The pictures you saw above were all made with diffraction gratings, not just a single slit. Now what about light that passes through a small hole? Here we have a circular edge all around the hole. Diffraction fringes form at an edge, and so we see these fringes inside and outside the circle. If light passes over an object that is nearly as small as the wavelength of the light, then diffraction fringes form around the outline of the object. Here you see the tip of a very fine wire. Notice the diffraction fringes around it. This diffraction around small things is interesting, but it is also a problem for scientists who design optical instruments like microscopes. A microscope is meant to make small things look bigger and clearer. But when you look through a microscope at very small things, which are nearly the size of wavelength of the light, then you see diffraction rings around them. Look at the diffraction rings around the small objects to the side of the central object. A microscope can show you 2 points on the object separately only if the 2 points are further apart than the wavelength of the light you use. Diffraction causes a similar problem with telescopes. A telescope needs to have a very wide light collecting surface because otherwise diffraction blurs the images you can get from it. This is also true for radio wave telescopes. The square kilometer array telescope has to be as big as a square kilometer in order to make clear pictures from the radio waves the stars emit. However, diffraction helps us in another way to learn about the stars out there. Each element in gaseous state, when heated, will give off radiation. Here you see some hydrogen gas with an electric current passing through it. The hydrogen atoms take energy from the current and then radiate the energy again as light. You have seen this happen in neon gas strip lights in classrooms and neon advertising signs. A gas radiates the energy of the current again, but only at certain frequencies and colors. A diffraction grating shows up the special frequencies as a spectrum with a few bright lines. Here is an example of what you see through a diffraction grating. The colored lines in the picture are the special colors that hydrogen emits. Hydrogen, no matter where it is, on Earth or in space, produces a pattern of frequencies that one can recognize. These colored lines are called the spectral lines of hydrogen. They are like the fingerprint of hydrogen. Each element in gaseous form has its own set of spectral lines, like a fingerprint of that particular element. Here you see the spectral lines of hydrogen, helium, neon, sodium, and mercury. Using these spectral lines, we can identify those elements by the frequencies of the light each gas radiates. From the spectral line photos, astronomers have worked out that hydrogen is the most plentiful substance in the universe. That is the substance stars are made of. We also know that hydrogen is converted to helium in the stars like our sun, and that conversion is what releases the energy we receive from the sun. And that's all for this lesson. Don't forget to check out other videos in this series, especially the task video. Also look at the Mindset website at www.mindset.co.za/learn. Until next time, take care.